Electric fields are relatively tough for a lot of people to understand. So I want to have this video for you to look at and to get good at those basics of how you know where they point, how you know how big they are, how you find the net electric field. That way, the harder problems, you're totally fine on the basics. So just a quick refresher on the electric field created by a point charge. Notice that I've boxed a few parts of this definition as very important. The whole idea of electric fields is that they're created by one charge and they exist technically out to infinity. So if I'm a charged particle, I create an electric field literally everywhere in the universe. Now we mostly care about it near me, but the electric field is everywhere. And so these things that we're dealing with, this electric field, if we're calculating a value, we're not calculating the electric field value. We're calculating the electric field value right here, or right here, or right here. We're calculating the field at exact places. And we're only doing it one charge at a time. So if Mr. Ayers comes over here and stands near me, we would have to calculate my field and do something, and then his field and do the same thing. We have to do two separate problems. We can't just magically combine them into one big monster problem. So it's only one charge that creates a field, and it's created at an exact location. Now, I've got a positive charge right here, 4 points, A, B, C, D. Now, you should know from that vocab quiz and from class that field lines point away from positive charges, because if you put a positive charge near there, it's going to be repelled. So these are at different locations, and they're at different distances, which you can see affects the electric field. Bigger distance means a smaller electric field value. So here, I can just have some standard vector, some standard electric field value pointing away from the positive charge. Notice that this distance creates a vector of about that size. Here I have a much bigger distance, and it's some diagonal location away from the positive charge. Since it's a positive charge, the field line will still point away from that, but it's going to be much smaller because we're farther away. Point C, again, same logic. It's going to point away from the positive charge. Notice that when I changed points, I stopped caring what B and A were doing. I only care about this charge's effect on point C now. Since it's so much closer, it's going to have a very large electric field value. And again, it will point down away from the charge. Here, I have point D. Point D, we're doing that diagonal thing again. We're still going to point away. But notice now that those are about the same distance, which means the field value should be the same strength, just at a different angle, because, again, always away from the positive. A has no effect on D. B has no effect on A. These points don't affect each other at all. It's just the charge affecting all of those separate points at the same time. We can just choose to focus in on those points depending on what the problem is asking us. All right, first math situation up here. I've got two positive charges. They're very big positive charges. Coulombs are huge. And I want us to find the electric field value at point P, the net electric field. Now, we know net from the whole year. It means some combination of stuff. In this case, it's the combination of the field from this charge and the field from this charge. So the field from 5 and the field from 9. Those are going to combine somehow right here and create a net value. Now, the important thing, anytime you're using any of these electric field or force equations, is that we have the math, we have the physics. The math tells us the magnitude, the number, tells us how strong that field is. The physics, we have to do the thinking. We have to set up our problem so that we get the correct positives and negatives. And then we can plug everything in as positive. So the first thing we need to think about here is when we combine these, which way are the different fields going to point? Well, think about what we just did. Fields point away from positive charges towards negative charges. These are both positive. At this point, at point P, the 5 Coulomb charge is going to create a field away from itself. And so at point P, that field value will be pointing to the right. So we're going to have the value pointing off to the right. Notice how big I drew that arrow. Then we have the 9 Coulomb charge. It is a positive charge, which means its field points away from itself. So away from 9 coulombs, away from that charge, is off to the left, away from the positive. Notice that I drew this arrow much, much bigger. We can pretty reasonably predict that this is a bigger field because it's closer and it's a much bigger charge. We have a direct relationship right there, an inverse square relationship with R, meaning the bigger charge and the smaller distance create a much bigger electric field value. And then from here, we pick our direction. We figured out which way these are going. Now we pick our direction. Which way is positive, which way is negative. I see no reason to make left positive, so let's just stick with our standard to the right. We'll say the right is positive, which means that when we combine these, we're going to get this electric field minus this electric field. positive this field minus this field pointing off to the left. So now we have our two things, and from here, it just becomes a matter of plugging in numbers and actually solving. Now, we have formulas for both of these, so from here we just got to plug and chug. K times the 5 coulombs over r squared minus K times the 9 coulombs over the other r squared. Now notice I didn't plug in numbers there, guys. I want to talk about that. We like to give you problems where we don't give you every distance explicitly. Most of the times it's pretty easy to figure it out, but we like adding that one extra step of thinking it. Here, I have actually given you the distance. The distance from the 9 coulomb charge to the point, so the r for the 9 coulomb charge, easy 2 meters. But for the distance from the 5 coulomb charge, there's one extra step. There's another step of thinking. If the whole thing is 7, and this is 2, that means that this distance has to be 7 minus 2. So 5 meters. Now I wrote it like this. You'll see why in the next bit. But thinking about it in this standpoint is really, really helpful for variable problems, for equilibrium problems, for lots of different ways. So always be thinking about this from the standpoint of the whole chunk, the whole thing, minus a little bit. That'll help you out a lot in the future. So we can do our 7 minus 2. We end up with 5 squared. Plug stuff in, blah, blah, blah. Get an answer. We're going to get a negative answer here. I don't know what the number is. It doesn't much matter to me. But we're going to get negative something newtons per coulomb. So think about what that negative means. A lot of times for electric fields, you're going to be asked, find the magnitude, find the direction. How big is it? Which way does it point? So it is a number big. It's that big. And then the negative, remember earlier we picked right as positive? The negative means left. So we could say the field value is negative whatever with the understanding that right is positive. But you need to indicate what your direction is. Draw a little coordinate system. Do something to indicate that that negative means left. Or just literally write down it's this number to the left. Do something to indicate that direction. New situation. 2 charges, both still positive. The question is being asked, where is the net electric field 0? Where do these combine to equal 0? Or you might see that phrased another way. Where can we put some other hypothetical third charge where it would feel 0 force? Now, that's asking the same thing, because we know that our basic field model is that a charge creates a field, and then the field acts to create a force on some other charge. So like, in this scenario with these 2 charges, this charge is not necessarily acting on this charge directly. It creates a field, then the field creates the force. So when you're asked a question, where would the third charge feel no force? Really what you're being asked is, where is the electric field 0? Where do the electric fields cancel out and produce no field? So the first thing you need to do is make that prediction. Think about, okay, where is it probably going to be? Well, we just talked about that the small charge produces a smaller field, and a bigger distance produces a smaller field. So we need to find that point in the middle. We should make the prediction of where they're going to cancel out. Now, let's say we pick some random point in the middle. Well, at the point in the middle, the distances are the same, which means the charge is the only thing that really matters for this choice. 2 is smaller than 5, which means at this location, 2 will produce a smaller field, so it won't be 0 right here, because the 5 will be too big. The 5 coulomb field will be too big, which means we need to move closer to 2 to both make this field bigger and this field smaller, so that they cancel out. So we'll be somewhere over here. We don't know where exactly. The exact point doesn't matter. We just want to make some kind of prediction, some vague spot, call it point P like we always do. We're going to say it's right about there. And we're going to say that this distance is x. We don't know how big it is, but we're going to call it x, which, think about the 7 minus 2 from the last problem, means this other distance is 10 minus x. Now we can finally set up and start solving. We have a point. We have enough information labeled to calculate 2 electric fields. We're basically home free at this point. Just a little bit of algebra to our answer. Trying to find this, we know that the fields cancel out. Since they cancel out, they have to be equal to each other. That's what equilibrium means. It means that the values are equal and opposite, adding up to 0. So we can say that the electric field from 2 is equal to the electric field from the 5 coulomb charge. From here, we can expand. K times this Q, 2 over r squared, we called rx, equals K times 5 coulombs over the r squared. our r squared is 10 minus x. And so from here, we need to solve for x. We have only one unknown. Now, when I write out k's, the k's are going to cancel. So from here, we just rearrange stuff. This, we can multiply up to the top left. This, we can multiply up to the top right, giving us this scenario. 2 times 10 minus x squared equals 5x squared. Now, from here, this is algebra that you should feel comfortable with. It's not the nicest algebra in the world, but it is definitely solvable. This we can solve with FOILing. This is just 5x squared. You can rearrange, might have to do a little bit of a quadratic equation to solve it, that's fine. But we just have to solve. Now, the bell's about to ring, so I don't actually have time to go through all of this. But this is algebra, again, I want to emphasize, you should be able to solve this. If not, come into tutorials right away. The big part of this, the hard part, is knowing to set this up. Knowing to say this is x and 10 minus x, and then knowing to set up with the field values to cancel everything that needs canceling, and then rearrange it and do the algebra. But that's the key part of this problem. You will have homework over the weekend. Use this to help you out. Hopefully you are. See you guys on Monday.